Hey, it's my pleasure to introduce Dr. Rajeev Thakur, who is giving a keynote speech on AuroraGPT. He is Argonne Distinguished Fellow and Deputy Director of the Data Science and Learning Division at the Argonne National Laboratory. And he received a Ph.D. from Syracuse a long time ago and has been working with MPI, ROMIO implementation in MPI-IO. And I also had the privilege of him being my mentor a long time ago. And thank you, Rajeev, for agreeing to give this talk. And please take over. Thank you.
Okay, thanks, Suren. Can you see the slides okay and hear me okay?
Yes, all good. Thank you.
Okay, great. So thanks for inviting me to give this talk. And I'm sorry that I couldn't be there in person. I had intended to be there in person, though. So Suren asked me to talk about the AuroraGPT project, which is a new project at Argonne involving many people, and it's about developing a large-scale AI foundation model for science. So these are the topics I want to cover today. Why do we need an AI assistant for science or foundation model for science in the first place when there's so much AI activity already going on in industry? I want to cover a little bit or at least point you to recent efforts in DOE. By recent, I mean in the past 3 to 5 years, at gathering community input on AI for science. And there have been many workshops and reports on that topic. Then I'll talk about the AuroraGPT project. And then I want to talk about an upcoming DOE effort, or that's in the planning stages, or hopefully it'll be a future effort called FAST. That's a big AI initiative. And then another effort that is an international collaboration, sort of a worldwide almost collaboration of interested people in this kind of AI for science. It's called the Trillion Parameter Consortium. So first, why do we need an AI assistant for science? So I don't need to say a whole lot about this, that AI models and foundation models have made a huge impact just in the past 2-3 years that we have seen them, or we have had access to them. The least of which is the GPT that came out, Chat GPT that came out a couple of years ago. But there are other equally capable models that are out now from Google and Meta and others in industry. And we've all seen how we have often been surprised by how good is their output. And sometimes it's not so good either. So there is room for improvement, and the newer, more capable models are getting quite surprisingly good. And it's also, we have seen advances in other areas such as self-driving cars. For example, with the latest software updates for self-driving cars, they've gotten quite good, quite capable. So it's not a stretch to imagine that if AI was applied in a scientific research domain, it could help us quite a bit to accelerate scientific research and scientific discovery in ways that we could not just do by old methods. And Argonne is interested in developing AI foundation models that are specifically optimized and tuned for science and scientific research. So what do we mean by an AI scientific assistant? So it's an AI-based system that has been trained on scientific data, and it has scientific skills such as reasoning, mathematical skills. We have seen that the current models are not so good at math, for example, the publicly available models. It understands the literature and so forth. And it doesn't have the hallucination characteristics that we see in other models. And they're getting better, no doubt, but we need less of that. It has a way of interacting with humans and even automated systems and automated robotic labs and so forth. And it has a degree of autonomy that is instead of starting with just repeating learned workflows, it can even develop the workflow. And it's capable of generating new hypotheses because if it has an awareness of the literature and is able to deduce something from it, it can generate new hypotheses as well. So for example, this is what an AI assistant for computational science may look like. The bullets on this slide show the typical steps in formulating and solving a problem in computational science. And you start off with some open problem or some problem that you want to solve. Then you come up with a mathematical formulation of the problem. Then there is a numerical or symbolic formulation of it. Then you need an efficient algorithm to implement it numerically. And if you're running on a parallel system, you need a parallel high performance computing implementation. You need a tuned and optimized version of it as well to run at large scale. You need to analyze the output, and then you sort of get insights from your results, or you close the loop on the open problem. Now, is it possible to build an AI assistant that could do all of this for you, starting with an open problem or starting with even defining what the open problem might be? So we're not there today for sure. I mean, the AI today could do some of these steps partially and maybe not even a great job at that. But the goal is, can we get more of this into in an automated AI assistant? And similarly, in the computer science field, we could have an AI scientific assistant that is not just for generating code. And we have seen with tools such as the GitHub Copilot or the AWS what's it called, Code Whisperer, and they're quite good at generating code, and they are improving programmer productivity for sure. Although it's not free of bugs, and you still have to be careful about what code that it produces for you or it suggests for you, but it's getting a lot better. But in the CS research area itself, there are many fields that involve optimization, like scheduling or performance optimization or energy optimization, where also these problems that are formulated as optimization problems can, AI could help in solving those. So what are foundation models, and what do we mean by that? Is that at a large scale machine learning model that is trained on large data sets from many sources, texts, papers, code. The ones from industry are trained on whatever data they can find publicly. But they need some additional training to improve the human interaction experience, that is to make them serve as a chat assistant or some other kind of assistant. And we have seen that these models that are trained on large amounts of general data, they turn out to be quite flexible and often also exhibit emergent behaviors. That is, they are able to do things that they were not specifically trained to do. They train on general things, but they're able to apply it to specific questions or specific tasks that you ask them to do later on. And so there can be many applications built on top of these. And there are many early efforts underway in DOE labs to create foundation models targeting scientific use cases for specific domains, such as in biology and so forth. So what is the opportunity here? So one is that a foundation model could summarize and distill knowledge, extract papers, information from all the papers that exist. So there's a lot of literature out there. It's almost impossible for any one person to read all the literature in their domain. Computer science is a relatively new field, but even in computer science, there is a tremendous amount of literature. And in the field of AI, there are hundreds of papers in archive every day. But in some of the other disciplines in engineering and in the other sciences, the literature goes back 50, 60, 70 years, which is it's almost impossible for a new student or anyone in the field to have read all that or have all of that in their brain. So they're selectively reading what they need to complete their thesis and so forth. Whereas an AI model could be trained, and with sufficient compute power, it could be trained on all of this, and it could somehow capture the knowledge available in all of this. They can similarly combine information from multiple sources, multiple papers or multiple, not just text sources, but other kinds of sources, and thereby suggest new hypotheses and provide new insights that would be difficult for a human to come up with. They could come up with, they can generate plans or solve logic problems or write protocols for robots and so forth, and powering self-driving labs. That's another area of interest at Argonne and other labs, namely automated labs, and generate hypotheses to be tested and perhaps explain, provide, try to solve some new problems or things that were not known earlier. There's a link at the bottom to this paper on the right which says, can ChatGPT be used to generate scientific hypotheses? And that's an interesting read if you haven't seen it yet. And one of the comments in that paper, it says that after experimenting with GPT-4 in our own research domains in materials, chemistry, physics, and quantum information, we find that GPT-4 is knowledgeable, frequently wrong, and interesting to talk to. In other words, it's not unlike a college professor or a colleague. So that's the current state of publicly available or commercially available foundation models when applied to science. But there's room to do better. Now, if you look at the kind of data that gets used to train these models, this is a figure that shows for the Palm model from Google that has 770 billion tokens. And it's a wide variety of data, and science is a relatively small portion of this. And if you see this box to the right, that is science, and it's trained on a whole bunch of other data. So they're not specifically scientifically, the scientific knowledge may not be encompassing all the literature or all the data that there is. So the opportunity here is to, or at least we think, is to have a specifically science-trained model. So what would such a model look like in open science? So it would be trained on a whole bunch of scientific and engineering data sets in all possible domains and papers from all possible domains. And many of these are available, or they can be obtained with some effort from places like Archive or PubMed or the ACM Digital Library and IEEE similar digital library and so forth. They need a whole bunch of compute resources, and we'll talk about that in a little bit. So there are Exascale systems at DOE labs. They're still not sufficient for this because those are also quite heavily used. But given sufficient compute, it's possible to build an open science foundation model that could be tuned for and adapted for various tasks downstream, such as code optimization or scientific discovery or digital twins or inverse problems and so forth. And that's the hypothesis. I wanted to touch on some of the community input gathering effort that has been going on in DOE for a few years. So in 2019, there were a bunch of town halls on AI for science that resulted in this report 2019 that came out in like February 2020 or so. These reports are available on this link that I have at the bottom. It's anl.gov and then AI-for-science-report. This was the first report that came out of this. And then 3 years later, there was another community input gathering effort. In 2022, there were 3 or 4 workshops that were held. And what has changed between 2019 and 2022 is that, or 23, is that the large language models got released and a chat GPT became available. People became aware of the potential or power of these foundation models. Artificial image generation took off in a big scale. You could generate images based on some text prompt. There were other success stories like AI folded 1 billion proteins. There were AI hints that AI was capable of advancing mathematics. There was significant improvement in computer programming, AI support for developing code and so forth. Lots of new AI hardware, including not just GPUs, but other specialized AI accelerators, and exascale systems started to arrive. So when this 2022 series of workshops took place, they were organized slightly differently, not by domain area, not by field or such, but more on cross-cutting areas that applied to various domains. So there was workshops that focused on inverse design, or AI and robotics for autonomous discovery, or surrogates, or prediction and control of complex systems. And each of those areas had multiple applications in them. And this report came out, I think, sometime early last year, that you can get from that site. And then late last year, like November, December, there was another workshop that focused more just on the energy part, because since DOE is Department of Energy, this was nuclear energy, power grid, and energy storage, energy materials. And this is the third report that got released earlier this year. So this was the sort of community community input gathering effort. I'll talk about the FAST initiative later on towards the end of my talk, because that's for the future. And then in October of last year, there was also a White House executive order on AI that specifically tasked DOE with a few things. So one is it says that the DOE is tasked with expanding partnerships with industry, academia, and other agencies, and also international partners, to use DOE's computing capabilities and AI testbeds to build foundation models that support new applications in science, et cetera. And it's also tasked as the lead agency through the NNSA to reduce risks at the intersection of AI and various security threats. So this is also a White House directive that on AI that for DOE to do certain things. So moving on to Aurora and AuroraGPT. So Aurora is as you know, is the exascale computer at Argonne, and this is the view that you see from the viewing deck. And if this meeting was held at Argonne, we could have shown you this system. We could even take you inside the machine room, the data center. So there are many racks of this. This is the first rack that you see, and there are several racks behind this. So Aurora is over 1 exaflop in HP LinPack, but it's over 10 exaflops in the mixed precision LinPack, which is more useful measure for AI purposes. So it's over 10 exaflops of the mixed precision arithmetic. But overall, it's a system with 166 racks, more than 10,000 nodes, more than 21,000 CPUs, and more than 63,000 Intel GPUs, and 85,000 NICs and so forth connected to Slingshot. And each Aurora, the compute blade, the diagram is shown on the right. Each node of that has 2 Intel CPUs and 6 Intel GPUs, and also 8 Slingshot 11 NICs connecting to the Slingshot network. So it's a very capable and powerful system, and that is what we want to use for training of these models. So this slide just shows an estimate of the time it might take to train some of these models. So for smaller models with say 7 billion parameters and 1 to 3 trillion tokens, it doesn't take a lot of time. The estimated time on Aurora in terms of hours is 1 to 3 hours. And on another system called Polaris that we have, which is a NVIDIA GPU cluster with around 560 nodes of NVIDIA A100 GPUs. I think there are four A100s on each node and 560 nodes. It's a fairly good capable system in itself, the Polaris. I think it's about 35 petaflops peak and 25 petaflops HPL. So it's a fairly big system. That takes a few days for this 7 billion parameter model. But as you scale up and you go to a trillion parameter model, or with tens of trillions of tokens, the estimated time even on capable systems like Aurora in days is like 68 days to 200 days. On Polaris, it's thousands, tens of thousands of days, which is really not feasible. So these models do take a lot of compute, and we don't really have that much compute, in the sense that these systems are being used for other things. They're quite heavily scheduled. There's the DOE Insight and ALCC allocations running on them. So they're almost completely utilized. So even finding the time, and we'll see that in a little later, getting time on these systems is difficult, and needing a lot of compute time is one of the challenges here. So AuroraGPT is it's named after the Aurora supercomputer because we want to use that. It is a general purpose scientific large language model that is broadly trained on scientific data, scientific papers and text, as well as structured science data. We want to design it to be safe and build a scientific assistant type of model. And we have international partners as well. Recon in Japan is one of them, and Barcelona Supercomputer Center is another one. The goal is to be multilingual, that is multiple languages: English, Japanese, French, German, and Spanish, Italian, and others as well. And multimodal eventually, not in the first year, not initially, but eventually multimodal, that it could have more than just text for training, other images, tables, and time series data, and other things. By the way, this is a project that has started maybe 6 months ago or so, and it's internally funded. It's right now it's LDRD funded, so it's it needs more funding as well. The goal is to build a series of models of various sizes, starting at 7 billion and 70 billion, and as we get more access to computing, larger models of up to a trillion parameters. And as I said, the phase one initially it would be text-oriented models, then going to basic multimodal models, and then more advanced scientific multimodal models. So how do these models get built? There's a nice video on YouTube, if you haven't yet had a chance to see it, by Andrei Karpathy from last year. And the title of it is, I think, State of GPT is the name of the video. And it's a talk he gave at one of the Microsoft events, where he talks about how models like GPT are trained in reality. So they go through a number of phases, or it's a pipeline. The first of which you can call pre-training, and this is the most compute intensive, or this is like the thing that takes the most resources and the time. Thousands of GPUs and months of training time, and where you feed it with the data, whatever is your training data set, and the model gets trained. But what comes out of it is a base model, or you can even call it pre-trained model, that in itself is not directly useful for what you might want to use it for. So there are other steps that it goes through, which are not super compute intensive. They are maybe about 100 GPUs and days of training, but they're used for fine tuning the model. Or if you want a chat specific model, then you need to, it has to be tuned for a chat type of purpose and so forth. So there are many stages to that effort. So similarly, we have structured the Aurora GPT effort into various teams that do different parts of this effort. So there's a overall planning group that I won't cover, but the other groups are the data group that is gathering the data to be trained and preparing it, getting it into a form that you can actually feed to the models, the training effort. There's a model training group. There is an evaluation group for evaluating how the model is doing. And then there's the post-training or the post-pre-training is what it's called, where you are specifically tuning that model for specific tasks, such as a scientific assistant or something. Then there is an inference group and two other groups on distribution and communication. So these are the people involved in it. The overall leads are Rick Stevens and Ian Foster. Then the data group is led by Ian Foster and Robert Underwood. The model training group is led by Sam Foreman and Venkat Vishwanath, and many of you know Venkat from his involvement in the HDF project, for example, in the ECP HDF project. Then there's an evaluation and safety group led by Frank Capello and Sandeep Madi Reddy, and also Bo Lee from U Chicago. And the post-pre-training group is Elio Huerta and Aston Wells. And I lead the inference group, and then there is distribution and communication as well. So just a little bit about each of these efforts. So the data group is tasked with collecting the data and pre-processing or processing it in a form that can be fed to the model training efforts. So there's a lot of data. Some of it it can be easily obtained. Some of them it takes a little bit of effort, but they have terabytes of data. I think some 14 terabytes or so far. So there are various of these data sets. RP1, RP2. DOLMA is another. It's a publicly available data set that can be used for training. Then on the scientific side, there are these chemistry papers, databases. There is the ACM Digital Archive. There is the archive and bio, med, and other chem archives and so forth. So they have downloaded a whole bunch of data. There's a lot of processing to do on this data because they come in PDF files, and you have to extract text from the PDF, which can be time consuming and take some. There are tools for it, but it takes some time. They also need to do deduplication of the data. So the data processing itself is when you're dealing with terabytes, is a significant amount of effort and challenge. Then there's the model training group, which is building trained this is actually pre-training, pre-trained models of this. So initially they're just starting with the DOLMA data set and a Llama 2 type of model and building it on Aurora and Polaris just to get started and get familiar and make sure that these models are building correctly and building on Polaris versus Aurora, you're getting a similar kind of result. So as you know, a lot of the AI software is it runs on NVIDIA GPUs, and there is plenty of open source software, plenty of researchers developing software, but it runs well on NVIDIA GPUs. Not all of it has been ported to Intel GPUs, and the software stack there can be differences. So some of those are some of the things they have to work through. They're using this Megatron Deep Speed, which works on the Intel side for distributed training. And their initial goal is to build an AuroraGPT 7B-A and a 7B-P, where A stands for Aurora and P stands for Polaris, and another version which is 7B-S, where S is for science. So these are the initial drops. It turns out that they're limited by the amount of compute time they currently have access to, because both are, Aurora is being, going through acceptance testing and so forth. And Polaris is in production, but is heavily used by inside ALCC and so forth. So they get smaller amounts of time than they need to or would like to. So they have to checkpoint and run again and so forth. So it takes a while to even train the smaller models right now. But we hope to have access to more compute in the future where we can do this pre-training sooner, quicker. Then there's this evaluation group, who's tasked with evaluating how these models are functioning and are they doing their job, and giving you the right answers, not hallucinating, and so forth. It turns out that this evaluation is a field in itself in AI, and there are tons of papers you can find just about how to evaluate models. One example is this decoding trust framework that comes from Bo Lee's group at U Chicago, and there are other efforts. So one of the things that this group is doing right now is they're building a benchmark. Let me get to it. Yeah, they're building a benchmark based on multi-choice questions that can be used to evaluate the trained model. One thing is that this benchmark itself should not be available for the model to train on, because if it trains on the benchmark, then it will do well on the benchmark. So it cannot be made easily accessible on the web. There has been some example of some other benchmark that was available, and then these commercial models or the chat GPT type models you trained on it and hence did better on it. So the benchmark ideally should not be directly accessible to the public models itself, or so that they don't it's like knowing the cheat sheet or the exam questions for an exam. So for this, to collect these questions, they have put together they're getting community input as such. They put together a web page for benchmark generation, and there was a hackathon held at Argonne with just the summer students 2-3 weeks ago, I think. And there is another one coming up with the staff where we're getting people together to add questions to this page. So what this says is what is a good question for this benchmark? So it should be a multiple choice question with only one correct answer. And the question is the level of it should not be a trivial question. It should be a level of the level of difficulty for a first-year graduate student. And along with the question, you submit the correct answer and 3 or 4 incorrect answers. And then you also provide the citation, or where does this question, where is the answer to this question, in which paper, or the DOI, or if it's an archive paper. And then you can also click on so this is, if you scroll down that form, this is, you give the correct answer, then the incorrect answers, and there are a few other things, and what's the level of difficulty. And you can even check, what, in a statistical way, what current models are doing for that. And not all the questions that we get are relevant or good or appropriate. So there's another step where you have to go and manually go and verify that these are the right kinds of questions that are useful for evaluating a scientific LLM. So that's the evaluation team. Then there is a pre-training team. And as I said, the model that comes out of the training is not directly useful. It goes through other steps, other fine-tuning, such as if you want a chat, a chat assistant or scientific assistant that can interact in a chat-like manner, you need to do some other processing and so forth. So there are techniques that are used for pre-training, which this group is working on. Then there's the inference group, which once you have these pre-trained and then post-pre-trained models, how do you serve them or provide them for end users of these models or applications? So there is software that for inference, such as VLLM or TensorRT LLM, or deep speed MII and so forth, which provide inference like services. And also you can provide quantized versions of these models, which are in lower precision, and so the inference can run quickly. So the inference team is delivering two things. One is optimized model runtimes that can be directly incorporated into custom programs, and also hosted services, inference services that provide access to these models via an API. And a commonly used API is there is an OpenAI API for it. I think it's called Chat Completions API. So that's commonly used by people wanting to do inference. And even within that, there are two approaches. One is a fast interactive version and a batch version where you can do many of these. So I've already covered this one, but in terms of the hosted inference services, one is a fast interactive API where it's almost like a chat type of model where you submit a query and you expect a response relatively quickly. And you need dedicated hardware for this, or you need hardware that let it be quick to respond. So this is one version of it. We don't have a whole lot of dedicated hardware right now that we can run this. We have to go through scheduling queues and so forth. So there is a second version that is more like a batch inference API where you can submit large batches of questions that can get scheduled, and then you get all your responses as a batch itself. So this is another effort from the inference team. And as I said, in terms of collaborators, we have one of our collaborators is BSC, Barcelona Supercomputing Center, and another one is RECON in Japan. And there was also an official MOU, Memorandum of Understanding, signed between Argonne and RECON. So here you see the Argonne director on the right and Rick Stevens having this virtual signing ceremony with Satoshi and others at RECON. And I'll talk more about this international collaborations as part of the Trillion Parameter Consortium as well. Just changing gears a little bit about an upcoming initiative from DOE called FAST. So if you go to this webpage called webpage energy.gov/FASST, FAST, that has this announcement or whatever from the DOE Office of Critical and Emerging Technologies about frontiers in artificial intelligence for science, security, and technology. That's what this initiative is called. It's a new effort that is in the planning stages and in the stages of securing funding or getting congressional approval or getting it in the congressional budget and so forth. So the budget for that is not yet there, but just recently, 2-3 weeks ago, a bill was introduced in the Senate by Senators Murkowski and Joe Manchin that proposes $12 billion over 5 years or $2.4 billion a year for DOE to work DOE's AI efforts. I think it's called the AI Act or something. So this has to go through the legislative process, and what it will turn out to be, we don't know as yet. So that page, which I mentioned on energy.gov FAST, has some more information about the FAST initiative. That is, it leverages DOE's enabling infrastructure and capabilities to deliver key assets for the national interest, such as to advance national security, attract and build a talented workforce, harness AI for scientific discovery. That's the AI for science. Address energy challenges, which is in a DOE's area, and develop technical expertise necessary for AI governance. And this initiative comprises 4 pillars, as they call it. It's data, compute platforms, models, and applications. So the data is DOE has a large amount of scientific data collected over many years, and it has experimental facilities, it has simulation data, it has a ton of scientific papers and so forth. Make all of that available to those building scientific AI models. Then on the compute side, DOE already has a good compute capability, but it's not enough for AI. And if you see the commercial industry has deployed hundreds of thousands of GPUs at Microsoft and Google and Meta. and also increasingly Tesla and X.AI, their GPU capability has probably now surpassed DOE, and DOE's computers are being used for the simulations and the the Insight and ALC. They're quite heavily utilized. So the second pillar is to build the AI compute capability at many of the national labs through GPU systems. Then the third one is to build safe, secure, and trustworthy AI models. And then fourth one is to build applications on top of these models that can solve important science, energy, and security challenges. So if all this goes through, and through the legislative process, then there will be a substantial effort involving all the DOE labs and also universities on AI for science. Then the next topic I wanted to cover is an international collaborative effort, which is not it's not a funded activity, but it's more a group of interested parties who are interested in AI foundation models. So it began 3-4 years ago with multiple organizations in Europe, Japan, and US who were interested in trillion parameter foundation models for science. And about sometime last year, maybe a year ago or slightly more, they created this virtual consortium called TPC, Trillion Parameter Consortium. And the website for it is tpc.dev, where you can go and see more information about it. It's an informal organization, and you can join it. I mean, it's my organization, and if your organization is not yet a member, you can join it. Just go to tpc.dev, and there's a link at the bottom on how to join or something, and it's a fairly informal. There's a form with only a little bit of information that you can join quite easily. So the goal is to build an open international community, incubate, launch, and loosely coordinate various projects, and create a global network of resources and expertise. And just in the short while of a year or more, there are probably 80 or so organizations that have joined this. And it's across the world. So the ones in green are organizations in the Asia Pacific region, that is Japan, Korea, Singapore, Australia, New Zealand places. Then the red is in Europe, and blue is North America, Canada, US, Canada type of places. So if you'd like to be a member, as I said, you can join quite easily from that website. Once you join, then you can get added to the Slack space for TPC, which has grown substantially. It has more than 1,000 individuals on it now. This one shows about 800, but I checked in; it's more than 1,000 right now. There are various subgroups there. Various Slack channels on specific topics. So whatever interests you, there are channels to talk to others in the community who are interested in similar things. And there are different working groups that have been set up, such as the model architecture and performance, data training, workflows, skills, safety, and so forth, and some more. There is a bi-weekly distinguished seminar series, and this is open to everybody. You can go online and join it via Zoom. The previous one's recording is also available. So you go to the events page on the tpc.dev website. You can look at the past seminars and so forth. There have been some get-togethers or workshops. So for example, there was a small event at SC last year, but there was a bigger gathering at ISC in May in Hamburg this year. And then there was a European kickoff workshop in Barcelona in June that had more than 180 participants from 17 countries. And there were 8 working groups met in Barcelona, and there are various follow-on activities through Slack and so forth. So this kind of effort, informal international collaborative effort, will continue. There is a workshop at SC in November It's a half-day workshop on Friday morning. So if you are interested and can stay on Friday, there is the TPC workshop Friday morning, half day. And there are other events planned this year and next year. Charlie Catlett at Argonne coordinates the TPC activity. So if you have any questions, you can reach out to Charlie. You can also contact me and go to their website. One last thing is that just some recommended reading in case you have not seen this paper or article so far. There is something called Situational Awareness: The Decade Ahead, and this is the link for that article. You can download it as a PDF file. It's about 150 pages or so, but you can also read it on this website itself. So it's an article by Leopold Aschenbrenner, who used to work at OpenAI, and now he's doing something else. He's a young person, but it's an industry insider's view of what is going on in the AI foundation model, large language model space, and where things are headed just over the next 5 to 10 years in terms of the capabilities of these models, in terms of the compute demand from them, the amount of GPU compute that expected just in the next few years. It's on an exponential curve. The amount of electricity that would be needed for it, and some of these companies are going and securing all the power contracts, all the spare power capacity that they can get to run these systems, and how close we might be to AGI or artificial general intelligence and so forth. So it's sort of an industry insider's view that somebody on the outside may not be aware of or may not know. So I highly recommend reading this. And then just to conclude, I would say that these are exciting times to be in the computing field, because we have a new application now, AI, that is changing things, and we have seen how it is changing things. And there is this AI industry which is racing far ahead, but it's not necessarily focusing on science or scientific research or so forth. So although we cannot match the pace of the investment and so forth of the industry, there is a niche, there is an area for the scientific community to use AI and to leverage AI for scientific research in ways that we may not have imagined a few years ago. And this AuroraGPT project aims to build such a foundation model that can catalyze advancements in science and engineering in general. So that's all I have in terms of slides. I'm happy to answer any questions.
Could you comment on how receptive the publishers are to your research or this AI in terms of, I mean, as you said, instead of going to a journal now, you just add AI, right? That's why it passed the journals and the publishers. And did you foresee then that the training model will not be open because of concerns about copyright and stuff like that? Can you comment on that?
Yeah, so I couldn't hear it clearly, the question. Can somebody repeat it? There's some distortion because it's coming from the room, I think. Could somebody summarize what the question?
You hear me now?
Yeah, I can hear you now. Better. Yeah.
I was just asking how receptive the journals or publishers are to this work in terms of, as you mentioned, that instead of going to the journal itself, you just type in an AI, and of course you're digitizing and doing all the papers. And do you foresee then, for copyright reasons, that the training model not be open to everyone? How does that impact it?
Yeah, so that's a good point, and I would say some are more receptive than others. Some take a little more of convincing, and the data could come with some conditions and so forth. So I believe we were able to get the ACM data. At least it took some time, and it took talking to the right people. I think more and more publishers would I think welcome this because they'll realize the value of it. And there is already a lot of data through archive, and then there are various there are variants of archive. There is the med archive, and some other fields there are archives. So even if you start with the data that is already relatively easily available, and the others that can be obtained with some effort, that itself is a lot of data right now, that enough to train models. And see, this is a rapidly evolving field, and the models that we build are also going to get better, and we need to get started with something and learn from it. I mean, we're all learning as we go. Many of us are new. I mean, all of us are new to this field as such, and it's moving so fast. So we can add more data. I think we could train models with more data as it comes along, but what is there itself is substantial, and a model that is trained on that would itself be quite capable, I think.
Looks like our audio is not working. The room audio is not working. If you have any questions, come to the front here. Okay. In the meanwhile, I have one question about the AI assistant or science assistant model for you. This. Do you also envision or any thoughts on the AI scientist model itself? So,
and by AI scientist, what do you mean?
not just being an assistant for scientists, but being a scientist.
Yeah, I mean, as the assistant gets more capable, it might feel like a scientist, but I think we're a long way away from that. Right now, if we can get it to help us in the next 5 years, if we are able to get it to work as an assistant or better than what we might imagine from an assistant, I think that itself would be a good first step. I mean, the good first thing is that if it has the knowledge of a large number of papers in the field, or most of the papers in the field, and is able to find some things, connections, or something out of it that we ourselves cannot. I think that itself would be a good first step.
So I was kind of alluding to right now, the AI assistant is only going to distill the PDFs and text, etc. There is a ton of data. Data is processing and analyze the data, such as data in HDF file.
Yeah, but I could again not hear it fully or clearly, but if you look at what the other foundation models or this chat GPT type of models, they're doing, they're training on whatever they can find, but based on that, they are now able to come up with things that they were not specifically trained on. They're able to do somewhat apply. It's almost like as if they've gained some knowledge that they're able to apply it to other things. So the hope is that a model trained for a scientific model is able to come up with new hypotheses or new theories or new explanations, or at least suggest some things that we could pursue further.
Okay. Any other questions? Okay, let's thank Rajeev one more time.